Welcome back once again. Justin Miller here, Oxnard College Physics. Today, in this session, we will be looking at the spring force, the force that a spring exerts on its surroundings. So we're going to look at a particular type of spring known as a linear spring. The force that a linear spring exerts is directly proportional to how much the spring is compressed by or is stretched by. So let me do a little example here. First off, got some springs, lots of different types of springs. Some that are really springy, some that aren't so springy, some that can only be stretched, like this one, pretty tough to stretch. Some that can be compressed or stretched. This one, another compression type of spring where I can compress it. Maybe not the easiest thing to see, but another spring. And I got some other colored springs. I got springs. Got this one's really hard to stretch. I can't even do it. But anyways, still a spring. What we want to do is look at this action of the spring force. So I got a little scale here that measures out force in newtons. I can attach this here spring to the scale. And what I want you to do is look at what happens as I stretch this spring more and more. What happens to the needle here? Right now it's reading about 3 newtons. I stretch it more. Ooh, now it's reading about 4 newtons. I stretch it more. Now it's about 6, 7 newtons. And that's about as far as I can stretch this particular spring. But the point is, the more that it's stretched, the greater that it pulls on the scale here. The greater the force it exerts on its surroundings. The less that it's stretched by, the less force. So I could take another spring and do sort of the same thing under a little bit different spatial extent and just see. So I stretch it more and more, the needle deflects more and more. And for a linear spring, we have that the spring force itself is directly proportional to how much the spring has been stretched by. That is, to double the amount that the spring's been stretched by, you have to double the amount of force, or you double the force it exerts on its surroundings. So what I'm going to do is take a couple different springs here. I'll take a green one, a red one, and a blue one, kind of set them up here, and look at how these 3 springs behave differently. Now, right now they're all about the same length, same natural lengths here. I'm going to go ahead and put a little mass hanger on each one. Move this side over a little bit. And then I'm going to place masses, 500 gram masses on each one of these. So we're going to have equal masses under the action of gravity pulling down on these springs. So when we take this red one here, put the mass on there, and what happens? If I let go, I bring it down to rest, and it's stretched by some amount. At this point right here, we have the force that the spring is exerting upward is exactly equal to the force that gravity is pulling down with. So we have the spring force is equal to mg in this case. When we do the same thing to this, same mg, so ultimately we have the same spring force between these 2 springs, but notice this one didn't stretch as much. Why? Because it behaves a little bit differently, but it still builds up the amount of force as it stretches more and more. Likewise, I can do this one. This one doesn't stretch as much as either of them in order to produce the same amount of force. So what we have is some characteristic of the spring that inevitably dictates how much the spring needs to stretch to exert a certain amount of force. And that characterization is known as the spring constant of the spring. So for a linear spring, spring force is given by F sub s hat is equal to negative k x hat, where k is called the spring constant. or force constant of the spring. X hat is the amount the spring's compressed or stretched by from its equilibrium position. Now let's just say that it's the displacement of the spring relative to equilibrium. Relative to the spring's equilibrium position. Which is defined as x is equal to 0. So what we want to do is measure all displacements of the spring relative to the equilibrium position, which traces back ultimately to the natural length of the spring itself. Measure things from there, and this gives us what the spring force is. Notice that there is a negative sign here between the direction of the spring force and the direction of the displacement. This is important. It says that the spring force is always back towards equilibrium. That is, take a spring and I pull it out that way, the spring force is back inward towards me, the opposite direction that it's been displaced by. You take a spring and you take it and compress it, the spring force is out that way, while the displacement of the spring was that way. How do I know? I let go of it, it goes back to its natural length. Take it here, let go of it, it goes back to its natural length. Equilibrium position of the system. So this is what we're going to do with springs, and for now, just really concentrate on the spring force itself. So let's do that. All right, so let's just ask ourselves a question, and then we can kind of investigate some of the stuff with the spring constant and aspects of a linear spring. Say that we got this spring, and it takes 25 newtons of force to stretch that linear spring by 0.130 meters. We want to know what's the spring constant of this spring. Let's go ahead and take something. We've got some spring here, and we've got some applied force that's stretching the spring. Normally, the spring just looks like this. We apply this force to it and we stretch it by this 0.130 meters. So I could call this x equals 0, the equilibrium position of the system, and then note that the spring has been displaced x hat, that much, relative again to equilibrium. So in our particular case, x is equal to 0.130 meters, and directionally it's in the direction of the force itself. Well, we've also got something else going on. As we stretch this spring this way, the spring exerts a force back on whatever's stretching it. So when we're over here, we've got that there is a spring force back in the opposite direction, wanting to restore the spring back to its natural length. So with this, if held at rest, we have the net force acting has to be equal to 0, and the net force acting will be the spring force plus the applied force, which merely just says the spring force and the applied force are equal in magnitudes, opposite directions. applied hat is then equal to kx hat, negative minus kx hat. So this is what we get. Well, with this, we can go ahead and solve this out for k. We've got that k is going to be equal to the force responsible for stretching the spring divided by the amount that it has been stretched by. So what do we get out of this? Well, we had 25 Newton force, made this spring stretch by 0.130 meters, which gives us K being equal to 192.3. 192.3. What are the units? Well, let's just look what it's composed of. It's the ratio of force divided by displacement. That's newtons per meter. Those are the SI units of spring constants, newtons per meter. Spring constant itself gives us valuable information once it is well defined. This says that if you want to stretch the spring by a meter, it will take 192.3 newtons of force to do so. If you want to stretch it by half a meter, it's going to take half that force. By a quarter of a meter, a quarter of that force. There's the direct proportionality with respect to the force that the spring exerts when it's stretched or compressed by a certain amount. And that's it. Linear springs behave very nicely. There's all other types of springs that don't behave linearly. The only thing we're focusing our attention on is truly linear springs. We get this linear responsiveness. And we'll be coming back to springs when we start looking at some other aspects, like making springs do some things. Like, what about if I take something, shoot it off with the spring? We use some catapults in class. Springs can do some stuff. So they exert forces, they can make other objects move. And that's what we'll be looking at a little bit more down the road. That's it for springs for now, though. Be well.